In this chapter, logarithms, we are going to be looking at this function called the logarithmic function. And if you are looking at logarithms for the very first time, it is possible that you will find the idea abstract, and this is normal, so please be patient. And my suggestion is, after we have learned logarithms together, please make sure that you spend adequate amount of time practicing it, because I believe that for an idea that is as abstract as this, it is only possible for us to completely internalize it with a lot of practice. So please make sure that you do that. And but I think the first thing that we should definitely do is to try to define exactly what is this logarithms. So if I were to be given this, y is equal to a to the power of x. This is in the exponential form. We talked about it in the chapter on exponential. We can actually re-express this into the logarithmic form, and that will look like this. This a y x. And this a here is called the base of the logarithmic function. This is the logarithmic function, and this is pronounced as logarithm to the base a of y, or just simply log to the base a of y. And this base, this a, has to be a number that is bigger than 0, but not any number that is bigger than 0. According to what I've defined here, yes, it can be any number that is bigger than 0, but it cannot be equal to 1. I mean, just imagine, if a is equal to 1, then 1 to the power of anything, it is going to be equal to 1, which means that y is also going to be equal to 1, which means that we are looking at 1 is equal to 1 all the time. So there's nothing much to discuss. Okay, so we are going to ignore a is equal to 1. And because a is a number that is a positive number, so a positive number to the power of anything will also be positive. That will make y positive all the time, which is what I wrote here also. And if the base happen to be either of these two specific numbers, then we actually have a dedicated notations for them. That will be when a, the base, is either e or 10. E is a constant. It is the Euler's number. We have discussed that in the chapter on exponential. It is just like pi. It is an irrational number. It is 2.71828 and so on. It is a number that cannot be expressed as one integer over another integer. So if a here happen to be e, then a notation that is like this can be used to represent this also. It is ln. This is called the natural log of x. So ln x, natural logarithm. And if a happen to be 10, the base happen to be 10, then we have a common log, and it is very commonly written as lg. So lgx, we will interpret it automatically as log to the base 10 of x. And why are we so interested in ln x and lgx? Because they are actually found in our calculator. Let me show you where it is. So on our calculator, here we have log. Log is actually lg in our syllabus. So this represents log to the base 10. So for example, we can definitely press this. Log to the base 10 of 3 is equal to this. Let me just press for another number. Log to the base, let's say 5. Okay, so sorry, this is log to the base 10 of 5. This is equal to 0.69 and so on. We can also press ln. So ln 6. For example, ln6, we can actually do a calculation for it. Later, we're going to see some questions where we are going to be pressing this ln and lg. So they will allow us to do some calculations. But please take note of them. They're actually going to be very, very useful here for this topic, because in this topic, what we are aiming to be able to do, after learning it, is to be able to manipulate an expression that has a logarithmic function in it, or to solve an equation that involves the logarithmic function. But before that, we do need to know some ways to arithmetically or algebraically do the manipulation. So I'm going to introduce to you 4 laws of logarithms. And the first law that I want to introduce is this thing called the product law. So the product law states this. The product law states that if we were to log to the base a of x times y, this is the same as log to the base a of x plus log to the base a of y. This can actually be very easily proven if I were to just use the definition of logarithms according to what we've discussed just now. If we were to just let this log to the base ax be equal to m, and if we were to let this log to the base ay be equal to n, then we can re-express this into the exponential form, and that will be a to the power of m this is equal to x. Similarly for this, a to the power of n, this is equal to y. And if I were to take a to the power of m, multiply by a to the power of n, this will be x times y. Then if I were to apply the law of indices that we have learned in the topic on exponential, then this will be a to the power of m plus n. This is x times y. So now we have an exponential form. We want to re-express this into the logarithmic form, and that will be log to the base a of xy is equal to m plus n. And what is m? M is actually this. So m, I'm going to rewrite it as log to the base a of x plus n. N is actually this, so I'm going to rewrite it as log to the base a of y. And now we have proven the product law. So log to the base a of x times y is log to the base a of x plus log to the base a of y. Let me show you a very easy example that how this can be applied. So if we have like what this example here says, log to the base 3 of 7x. So if we were to just try to split this up according to the law of logarithms in this product law here, then this can be rewritten as log to the base 3 of 7 plus log to the base 3 of x. Okay, it is very simple to be applied. Let me take a look at another law. It is called the quotient law. So quotient law states that if we are going to be doing a log to the base a of x over y. So here from x times y, we are going to change this to x over y. Then this is going to be equal to log to the base a of x minus log to the base a of y. I'm going to use a similar method to try to prove this. Again, it is actually very easy. It's a bit tedious, but I'm going to just make use of the definition again. So if I were to let this log to the base ax be, let's say m again, and I'm going to let this log to the base a y be n. So in its exponential form, this will be a to the power of m. This is going to be equal to x. In the exponential form, it will be a to the power of n. This is going to be equal to y. So if I were to now take a to the power of m divided by a to the power of n, it is going to be x over y. And again, by applying the law of indices, we can actually rewrite this as a to the power of m minus n. And this is going to be equal to x over y. So this is in its exponential form. We are going to rewrite it from the exponential form to the logarithm form. And that will be log to the base a of x over y. This is going to be equal to m minus n. And m is log to the base a of x, and n is log to the base a of y. So log to the base a of x over y is just simply log to the base a of x minus away log to the base a of y. This is our second law. Let me introduce to you, okay, before the third law, okay, let me just show you a very quick example also. So what if we have this? What if we have this ln of 4 minus x divided by x plus 5? Okay, log to the base e is ln, and very often ln is pronounced as ln. So this ln of 4 minus x over x plus 5, which, like what we were saying, it is log to the base e 4 minus x over x plus 5. But nobody really write this, okay? So let's stick to this. So if I were to just apply our quotient law, then this will be ln of 4 minus x minus ln of x plus 5. Okay, simple. So now we will look at the third law. This third law is the power law. Okay, this third law is very easy to prove. So for this power law, we are looking at log to the base a of x to the power of r. And this, according to power law, is going to be r times of log to the base a of x. And why is this so? I'm going to start with this. I have log to the base a of x to the power of r, which means that I can also rewrite this as log to the base a of x times x times x all the way until the very last x. It is just x times x times x times x. So for example, x to the power of 5, it will be x times x times x times x times x. How many have I done? Okay, 5 of them. Okay, 5 x's going to be multiplied together, which means that here we are going to be having how many x's being multiplied together? We're going to be having r number of x's being multiplied together. And if I were to apply what we have discussed in the product law, then this can be re-expressed as log to the base a of the first x plus log to the base a of the second x, and all the way until log to the base a of the rth x, because there are r number of them. So it will be 1, 2, 3, all the way, there are r number of them. So if I were to just add them together, it is going to be r number of log to the base a of x, and this has proven to me our power law. Log to the base a x to the power r is like r log to the base a of x. In a way, sometimes I think very commonly just sort of like described by students is sort of like to bring this r over to the front. It is something that is like this, okay? It will make it easier to memorize. The last law, again, example, okay? Let me show you an example. So power law, this is super easy. I don't think I even need to write it down for you. So if we have this common log, so common log of 4 plus x squared to the power of 5. Then this 5 can be brought to the front. It will be 5 common log of 4 plus x squared. And the last law that I want to talk about is very, very useful. Okay, this is going to be used a lot in O-level. It's going to be continued to be used in the A-level also. In fact, all these laws are going to be used in the A-levels. So this last one is called the change of base. So for this change of base law, it states that if we have log to the base a of b, then we can actually rewrite this as log to the base c of b divided by log to the base c of a. Now in the numerator and the denominator, we are doing the same base for the logarithmic function. So we're introducing a third constant, a third number into our log as the new base. Let me try to prove this to you also. So if we were to let log to the base a of b, if I were to let this be equal to x, and what I'm going to do is I'm going to try to re-express this. Okay, I'll let this be equal to x. I'll re-express this in its exponential form, and that will be a to the power of x. This is equal to b. A to the power of x is equal to b. And what if now I try to perform a logarithmic function on both sides? I'm going to choose the new base, and I'm going to choose it as a base c. So c can be any other c can be any numbers. So if I were to apply it to the left hand side, log to the base c of a to the power of x, this is log to the base c of b. And this x is the power. Applying the power law, I can bring x over to the front. This is going to be x log to the base c of a. This is log to the base c of b, which means that x is going to be equal to log to the base c of b divided by log to the base c of a. And what is x? X is this. So log to the base a of b is equal to log to the base c of b divided by log to the base c of a. This is the change of base law. Let's take a look at an example. So if we were to have a log to the base 8 of 11, if I want to just re-express it to a new base, then this can be written as log to the base 3. This is the new base, okay? Log to the base 3 of 11 divided by log to the base 3 of 8. You can choose your own base, so it need not be just 3. It can also be rewritten as log to the base, let's say 5 of 11 divided by log to the base 5 of 8. They're going to be the same thing, which means we can also choose e to be the new base. If I were to choose e to be the new base, then we are talking about ln 11 over ln 8. If you were to choose 10 as the new base, then it will be the common log of 11 divided by common log of 8. Let me just very quickly show you something, okay? We are looking at this. I'm saying that ln 11 over ln 8, or we can also see it as ln 11, the common log of 11 over the common log of 8. And they are actually equal. Okay, the notation that I use here is equal. So this is equal to this, which can also be equal to this, which can also be equal to this. Let me just show you a numerical verification of this. So for example, let me try to press this. The natural log of 11 divided by the natural log of 8. So it is going to be ln 11, close bracket, divided by ln of 8, close bracket. This is equal to 1.153 and so on. Let's try to see whether they are really equal, okay? So I'm going to try again. What if now I were to be using the common log? So common log of 11 divided by the common log of 8. I'm pressing for this, and this is going to be equal to the same thing. Okay, so we are talking about them being the same. That is why this C here can be any numbers. Of course, it must be a number that is bigger than 0. It must be a number that cannot be equal to 1, but it can be any other numbers that are bigger than 0 but not equal to 1. So we can choose this number ourselves. Again, this will still feel sort of like abstract because you cannot really see the actual application. So please be patient. We're going to look at some examples in a short while. But before we look at the examples, I want to introduce to you some more results. Okay, these results are also going to be very, very useful. These 3 results here, they're going to be very useful in order for us to be doing questions in our exams. First is this log to the base a of a is equal to 1. I'll suggest that you memorize this. Log to the base a of a is equal to 1. Why is this so? Let me show you the proof. I'm talking about this. Log to the base a of a is equal to 1. So let's say we are going to try and analyze this log to the base a of a, and we don't know that it is equal to 1. So I'm going to let this log to the base a of a be equal to y for now. And if I were to just try to re-express it into the exponential form, then this will be a to the power of y is going to be equal to a. And what is a? A is the same as a to the power of 1. So a to the power of y is equal to a to the power of 1, which makes y to be equal to 1. So what is y? Y is this. Log to the base a of a is equal to 1. Which means that if I have ln of e, this is going to be equal to 1. And please not forget what is ln e. Ln e is like log to the base e of e. So this is equal to 1. Which means that Lg, the common log of 10, is going to be Lg. This is going to be equal to 1. Let's just do a very quick verification. So if I were to go for, let's say, Lg, okay, so Lg on my calculator of 10, we are expecting a 1. Let's see whether it's going to be true. So this is going to be equal to 1. So please remember this. Another very, very useful result that I want you to remember is, what if I were to try to log to the base a of 1? Log to the base a of 1 is going to be equal to what? According to the useful result that I've stated here, it is going to be equal to 0. Please memorize this also. Let me just give you a very quick proof. I'm going to use the same idea to prove this. So this, I'm going to let it be equal to y, which means that a to the power of y is equal to 1. And hey, what is 1? 1 is a to the power of 0, right? We can re-express it, which means if I were to compare this and this, y is going to be equal to 0, and y is this log to the base a of 1. This is going to be equal to 0, which means if I were to log to the base e of 1, we're expecting a 0 also, right? Let's check it by making use of our calculator. Let's go for a ln 1, the natural log of 1. Yeah, 0. And the last one here. The last one here is very commonly missed out by students, but it's not as commonly tested. But the more when it is tested, if you are able to remember this, then it is going to be your advantage. That is why I will actually suggest that you please memorize this. This is also going to be very useful for A-level math anyway, so just memorize this, okay? Make sure that you know this. This says that a to the power of log to the base a of b. This is going to be equal to b. Okay, it's a bit weird, but a to the power of log to the base a of b is equal to b. So, which means that e to the power of log to the base e, which is ln of e. Okay, not e. E is just too confusing. Okay, too many e's over here. So e to the power of ln of, let's say, 2. What are we expecting this to be? We're expecting this to be equal to 2. E to the power of log to the base e of 2. According to this result, it should be equal to 2. Let's do a quick check to see whether this is going to be true. So this e to the power of, then ln. Okay, 2 is going to be equal to 2, so let's try to press 2. This is equal to 2. And if I were to just try, let's say, let me just try another number. I mean, although I believe that you have already been convinced, but let me just go for one more number. Let's say 1.5. Okay, what are we expecting this to be? 1.5 or 3 over 2. And why is this so? Let's take a look at a proof, a quick one also. We are going to be letting this a to the power of this. I'm going to let this be equal to y. So if I were to let this be equal to y, then if I were to log to the base a on both sides, log to the base a on both sides. So a, then log to the base a of b, and I'm going to log to the base a on the right hand side also. This is equal to y. And using power law says that this can be brought forth to the front, right? So we have a log to the base a of b. This is brought to the front, and what I'm going to be left with is log to the base a of a. This is log to the base a of y. And what is log to the base a of a? It is one of the useful results that we have just talked about. It is 1. So this is going to become 1. So we are going to be left with just log to the base a of b is equal to log to the base a of y. What is this showing me? This shows me that b and y, they are the same. So y is going to be equal to b, and what is y? Y is a to the power of log to the base a of b. So this is equal to b. And I think now we are equipped with enough information for us to start trying out some questions. So let's start to look at questions and see how this law of logarithms can be applied and how these few useful results that we have talked about here can be applied. I'm going to leave this here since this is the core definition of logarithms. Let's take a look at some questions. Let's take a look at this. So 1a. 1a, we want to show that this log to the base 2 of 16, we want to show that this is equal to 4. Let's see whether it is possible for us to get this by making use of the law of logarithms that we have learned, or the useful results. Okay, maybe we need to make use of this. And I think what I'm going to try make use of is this power law. And to do that, I'm going to re-express 16 as 2 to the power of 4. And applying the power law, or I can bring it forward, I will have log to the base 2 of 2. And then I'm going to apply this useful result. Log to the base a of a is equal to 1. So this is going to be 4 times of 1. So this is equal to 4. And the next question that I have require us to prove that this is equal to 147. Let me write it down. So we are looking at 7 to the power of 2 plus log to the base 7 of 3. We are supposed to prove that this is equal to 147. Okay, let's see whether we can do that by making use of the laws and the useful results that we have discussed. The first thing that I'm going to do is I'm going to use the law of indices to break this up into 7 to the power of 2, 7 to the power of log to the base 7 of 3. 7 to the power of 2 is 7 times 7, so this is 49. How about 7 to the power of log to the base 7 of 3? This, I'm going to use the useful result that we have discussed, which is this, the third useful result. So a to the power of log to the base a of b is equal to b, which means that 7 to the power of log to the base 7 of 3 is equal to 3, and 49 times 3 is 147. And one more, we are looking at this. Log to the base 1 over 5. Okay, this looks a little bit complicated. This plus 4 log to the base 3 of 243. This is the next question. And we are supposed to try prove this is equal to 18. This is our objective, okay, to prove that this is equal to 18. Let's see whether we are able to do that. And again, I'm going to try to make use of the few laws that we have discussed. So let me just flesh out the laws again. And I'm going to try to apply this change of base. Okay, you'll see why I will apply change of base later. So for this over here, I'm going to try to change its base. I mean, first of all, this base here just doesn't look very friendly. So I'm going to try to change this to something that is more friendly in terms of algebra. And I think I'm going to choose 5. Why am I choosing 5? Because 25 is 5 squared. And 1 over 5 is 5 to the power of minus 1. So if I were to choose 5 as the new base to change it to, then this will be log to the base 5 of 25 divided by log to the base 5 of 1 over 5 plus this. This I'm also going to do some changes to it. Log to the base 3 of 2, 4, 3 is actually 3 to the power of 5. So I'm going to re-express this as 3 to the power of 5. Okay? Then for 25, I'm also going to re-express it as 5 to the power of 2. And for this, I'm going to re-express 1 over 5 as 5 to the power of minus 1. And for this 5, I can actually bring it forward by making use of the power law that we have just discussed. So for this, I'm going to bring it forward. So plus 4 times of 5 times of, I'm going to be left with a log to the base 3 of 3. So what is this? 2, I can bring it forward. So it will be 2 times of log to the base 5 of 5 divided by minus 1. I can bring it forward using the power law. So minus 1 times log to the base 5 of 5 again, and plus 4 times 5, this is equal to 20. And what is log to the base 3 of 3? This is the useful result that we have discussed. Log to the base a of a is always going to be equal to 1. So this, I can either cancel it, or log to the base 5 of 5 is just 1. Log to the base 5 of 5 is also just 1. So we have a 2 divided by minus 1. It is going to be minus 2 plus this, log to the base 3 of 3. This is 1. So 20 times 1 is 20. So we have now with us a 18. Okay, this is what the question wants us to prove. Let's take a look at another question. Let's see what we have now. Okay, we are supposed to solve equations now, okay? And the first equation that we are going to be looking at is this. 5 to the power of x plus 3. This is equal to 23. Let's try to solve this equation. I mean, if 23 is easily expressed in the exponential form with the base as 5, then I think I will not have much of a problem. But too bad, it is very difficult for us to see how 23 can be re-expressed with 5 as the base in this exponential form. So what I'm going to do instead is I'm going to take this and I'm going to try to apply log on both the left and right hand side. We have done that just now when we were trying to do some proof. And the log that I'm going to try to make use of is going to be, I can either make use of either the natural log or the common log. Because later I'm going to show you, I can then press this into the calculator. Let me choose natural log first, okay? And I'm going to show you how that can be done. So if I were to apply the natural log to the left hand side, so this 5 to the power of x plus 3, I'm applying the natural log to it. So I'm going to try the same thing to the right hand side. So it will be ln of 23. And this can be brought forward using the power law. So we have x plus 3, it will be ln 5 is equal to ln of 23. Which means that x plus 3, this is going to be equal to ln of 23 divided by ln of 5. And now we can make x a subject. It is ln of 23, ln of 5 minus 3. And you know what? This we can actually press it directly into the calculator. Because from the calculator, we can just press this. Okay, let me just press. So it will be ln of 23 over ln of 5. So now since we have chosen ln, okay, if we have chosen some other log, for example, log to the base 7, then there will be no way for me to solve for this because I cannot press it into the calculator. So now I can do a natural log of 23 divided by, what do we have here? natural log of 5. So divided by ln of 5. Then we are going to take this and minus 3. And this will give us our answer. This is going to be equal to minus 1.05 3 significant figures. So what if you were to be thinking of like an alternative, okay? Because I have chosen the natural log here. What if I've chosen common log? Okay, I mean, if it is log of 5, log of 7 to the base 7, okay, those are out of the question because I cannot even use my calculator to resolve it. So I will either be choosing natural log, ln, or the common log, lg. So natural log works. What if I happen to choose the common log instead? Let's see whether it is going to work in the same way. So from here, I'm going to try to do a common log to the left-hand side. So 5 to the power of x plus 3. This is going to be this of 23. So this, again, using the power law, we can bring x plus 3 to the front. So we have this is equal to lg of 23, which means that x plus 3 is going to be lg of 23 divided by lg of 5. So x is lg of 23 divided by lg of 5 minus 3. I mean, it should give me the same answer. Let's try. So if I were to use the common log instead, so log of 23, close bracket, divided by the log of this is 5. So divided by this, then minus away 3. And we're getting the same answer. It is equal to minus 1.05. Okay, so when it comes to equation that is like this, please be assured, it doesn't really matter whether you are going to be using the natural log or the common log. They're going to lead you to the same answer. Let's take a look at another one. This one here, 2b. And in this 2b, we are looking at this. Log to the base 4 of x squared plus log to the base 4 of 2x cubed. This is equal to 3. And what I'm going to do is I'm going to use the product law. The product law states that if I have log to the base a of x times y, then it is going to be equal to log to the base a of x plus log to the base a of y. And now we have what we have just talked about but it is from the right hand side. So log to the base a of something plus log to the base a of something can also be re-expressed as log to that common base of x squared multiplied by 2x to the power of 3. This is equal to 3, which means that from here, we can actually rewrite this as log to the base 4 of this times this is 2 applying the law of indices. It will be 2 plus 3 as the new power, so 5. This is equal to 3. And now I'm going to try to re-express it from the logarithm form to the exponential form. So 2x to the power of 5, this is going to be equal to 4 to the power of 3. And 2x to the power of 5, this is equal to 64, which means that x to the power of 5, this is equal to 32. And 32 is just simply going to be 2 to the power of 5. Now comparing this, therefore we know that x is going to be equal to 2. And one last question. This one here, C. In part C, we are looking at this equation. Log to the base 5 of x is equal to 4 log to the base x of 5. Okay, now this looks complicated, but I think once you have seen an example, this can also be very easily done because no matter how intimidating the equation looks like, the manipulations will always be following the law of logarithms and making use of either of the three useful results. So what I'm going to try to do is I'm going to try to find a common base to the logarithmic function that exists in this equation. And the common base will be either x or 5. I think 5 sounds easier, right? So I'm going to choose 5, okay? So log to the base 5 of x. This is going to be 4. I'm going to do a change of base, and in case you need some prompting to apply this change of base, it is this. We can choose our own base, and I'm going to choose new base as 5. So this, I'm going to rewrite it as log to the base 5 of 5 divided by log to the base 5 of x. We carry out a change of base. So this will be log to the base 5 of x is equal to 4 times of what is log to the base 5 of 5? This is 1, right? Log to the base a of a is equal to 1 all the time. So this is going to be divided by log to the base 5 of x. And I'm going to multiply this across to the other side, which gives me log to the base 5 of x squared. This is equal to 4. There's a common mistake. Some students will try to bring this down to the front. This is not correct. You cannot bring the overall square to the front because this 2 is not governed by the law of logarithms. If you can bring it over to the front, then it has to look at like something that is this instead. Then this 2, yes, this you can bring it over to the front. Okay, but this power 2 remains at power 2. So how are you going to remove this power 2? We can do that by doing a square root on both sides. So log to the base 5, x is going to be this, is equal to square root this is going to be plus or minus 2, which means that we have log to the base 5 of x is either minus 2 or log to the base 5 of x is equal to 2. This tells me that x is equal to 5 to the power of minus 2. So this is 1 over 25. Then this x here is 5 to the power of 2. This is equal to 25. We should do a quick check also to just substitute this back into the original equation and see whether both the left and right hand side are going to be defined. So if I were to put this inside here, is it going to be defined? Yes, it is, because I just need to make sure that this number here is a positive number, so it is going to be defined. Will this work here? Yes, it will be, because this is a positive number and it's not equal to 1. I'll do the same thing for 25, just to make sure that both the answers are going to be acceptable. We have just done a few examples, and like what I was saying, these examples are probably not going to be enough for you to internalize this topic completely. So please remember, after we have finished this chapter together, please put in some effort, please put in more effort, okay, to practice this topic a lot. With more practice, I believe that it will then be internalized completely, and it is not going to be difficult. It just requires a bit more time. So please be patient also. Let me just introduce to you one last idea that is behind these logarithms, which is actually to sketch the graphs. The graph is a little bit strange because we are going to try to sketch the graph of y is equal to the logarithmic function. We're going to be discussing about sketching the graph of y is equal to log to the base a of x. Sketching the graph of this. Y is log to the base a of x. So we will definitely be sketching it on the xy axis, x-axis, y-axis. And when we're trying to sketch this onto the xy axis, we are actually going to be expecting two different forms, two different graphs. And that actually depends on the value of a that is in your logarithmic base. If this base here is bigger than 1, and then this is going to be the graph that you will be expecting, it is going to be an increasing graph, and this graph will be cutting the x-axis at 1, 0. Why 1, 0? Because if I were to find where it cuts the x-axis, that is when the y coordinate is equal to 0. So by letting log to the base ax be equal to 0, then x is going to be a to the power of 0, and a to the power of 0 is 1. That's why this point here is going to be 1, 0. And it will have a vertical asymptote, so the graph will tend towards x is equal to 0, but you will not touch x is equal to 0. So x is equal to 0 is going to be the vertical asymptote. It is a feature that is for the logarithmic graph. Okay, and please take note, this graph will look in this way if a is a number that is bigger than 1. And if a is a number that is between 0 and 1, I mean a cannot be equal to 1, a must be positive. So if it is not, a is bigger than 1, then if a is between 0 and 1, you are going to be getting a very different graph. It will become a decreasing graph. For this decreasing graph, it will still have an x-intercept at 1, 0, because to calculate this, we are still going to be letting log to the base ax be equal to 0, and we are still going to be deriving x is equal to 1. So this will not change, and at the same time, x, which is this here, just now we have discussed about it, it must be a number that is bigger than 0. It cannot be even equal to 0. So now we have a vertical asymptote, x is equal to 0. And what you need to do is to memorize the two versions of the graph and to replicate them again in the exam. And this is all I have for the topic on logarithms. And if you're okay with this, like what I was saying, please make sure that you try to practice a lot, try to take out as many questions as possible, and try to apply all the laws of logarithms and use the useful results that we have discussed to manipulate the expression and to solve the equations. And that is all that I have for logarithms. See you in the next chapter.